Here we look at the chemistry of acid anhydrides. And acid anhydrides are formed by the reaction between two carboxylic acids. I'm going to use ethanoic acid as my example. These two carboxylic acids are going to react, and in the process of reacting, they will kick out water, the H from one acid and the OH from another acid, and that will form my acid anhydride. And my side product of water. So we can see it's the CH3COO from one acid molecule and the CH3CO from another acid molecule. Now, because this is being derived from ethanoic acid, this molecule is called ethanoic anhydride. And we can see that we've got a CH3CO there and a CH3CO there, and then this additional oxygen. So this is written as, in a structural formula, CH3CO twice O. The reaction that they undergo is very similar to the one with acyl chlorides. Is very similar to the reaction we looked at with acyl chlorides. Again, I'm going to use ethanoic anhydride in all my examples. This acid anhydride can react with a nucleophile in just the same way as the acyl chloride does. So that's the reaction. What happens then is this here will tag on with this part of the nucleophile to produce this. Now that is exactly the same as what happens when acyl chlorides react with nucleophiles. It's this CH3CO will tag on with this to form my first product. And then all this bit here, highlighted in green, will then join with the hydrogen from the nucleophile. So it's basically the same reaction as with acyl chlorides, but instead of being a Cl, it's this CH3COO group. So instead of forming HCl, it's H and then this CH3COO group. So we get a carboxylic acid. Now, the nucleophiles that we need to be aware of are just the same as with the reaction of acyl chlorides. We've got H2O, NH3, alcohols and primary amines. So let's have a look at their reactions. I will say now that it does undergo nucleophilic addition elimination in much the same way as an acyl chloride. The mechanism is exactly the same, except this here is instead of the Cl. But we don't need to know the mechanism for the exam. But we might be asked to write down the reactions. So let's have a look. First is with water. So CH3CO2O, that's my ethanoic anhydride, and that reacts with water. So as we can see, if this Nu is OH, as it is with water, we get ethanoic acid. But we also get another ethanoic acid here, so we get two ethanoic acids. Second one is with, let's have a look with methanol. So this time my Nu is OCH3. So this is going to be OCH3, and therefore we're going to get an ester. And we always get ethanoic acid formed. Third reaction is with ammonia. And again we get ethanamide, and we always get ethanoic acid. And then the fourth reaction, remember, is with methylamine. And we get AN substituted amide. And of course ethanoic acid. Now the reactions here of ethanoic anhydride with these four nucleophiles is identical to that with ethanoyl chloride in the four nucleophiles. We get the same product here whether I use ethanoyl chloride or ethanoic anhydride. The difference being is my other products. Instead of forming HCl, we form ethanoic acid. But usually the desired product is nearly always what's highlighted here in yellow. So whether I use ethanoyl chloride or ethanoic anhydride, it doesn't make any difference. You get the same organic product, same important organic product. Now, this reaction is very useful in the synthesis of aspirin. So aspirin is made from a molecule called salicylic acid, which is 2-hydroxybenzoic acid, which has got the following structure. And we can react that with ethanoic anhydride. And we can see that we've actually got an alcohol. So if I compare it to this reaction here, which I've colour-coded, the Nu part, highlighted in blue, is actually now all this. And the H is there. And remember that we're going to add on to this blue part, this CH3CO, and then this bit I'm highlighting in green will tag on with the orange highlighted part of the hydrogen to form ethanoic acid. So my structure of my products will be as follows. And that there is aspirin. So let's colour code this. So that there is an example of where this reaction is useful. Now, you may ask, why would we use ethanoic anhydride? Why couldn't I use ethanol chloride? Well, it's better to use the anhydrides because they are cheaper and they don't produce corrosive fumes of HCl. There are other reasons why I would use it. They're not as moisture sensitive as well. They don't react as fast with water as ASR chlorides do. So that there is the chemistry of acid anhydrides. We've looked at how they're formed. The general reaction is pretty much the same as the one with ASR chlorides, but instead of a Cl, we've got this CH3COO group. And the reactions with the nucleophiles, we don't need to know the mechanism, but we do potentially need to know the reactions. I've looked at where the application of where this reaction is important will be something like the synthesis of aspirin, and why we would use an acid anhydride in a reaction rather than ASR chloride.